Hello there, my name is Paulina Hernandez Sainz, and today I have the pleasure of guiding you through my bachelor thesis research, Quantum Computing as a Tool for Gravitational Wave Analysis. Sounds fascinating, doesn't it? You might be wondering to yourself, why would anyone want to study such a niche intersection of highbrow concepts? Well, gravitational waves within them encode information about the stellar objects that generate them that we would not be able to access otherwise. Analyzing them, therefore, gives us better insight into the nature of these bodies and of gravity itself. On the other hand, quantum computing algorithms have a wide application all over science. As an example, the subroutine that we use, VQSVD, was originally designed for quantum chemistry, which has applications in molecular pharmacology, which helps create life-saving drugs. Quantum computing can also help us solve very complicated sets of differential equations that can allow us to model weather patterns and thus understand the impact of climate change better. But let's go back to the basics. Do you know what a gravitational wave is? Picture two ultramassive accelerating stellar objects. In our case, two black holes. These black holes have fallen into each other's gravitational well. This means that they will now start to spiral closer and closer and closer together until boom, they merge. As this happens, they release an enormous amount of energy in the form of gravitational radiation. All of this energy rushes outwards after the merger, in all directions and at the speed of light, undulating space-time as it travels. When these waves reach us, they are so teeny tiny that even Albert Einstein, who first predicted them in 1916, believed that they could never be studied. I'm, for once, happy to say that Albert Einstein was wrong. And thanks to enormous collaborative scientific efforts, we have been able to record and successfully flag over 60 gravitational wave signals since the first detection occurred in 2015. To achieve this awe-striking task, we use a network of gravitational wave interferometers placed all around the world that are both enormous and incredibly precise. This precision is necessary to record the changes in spacetime, which can be smaller than a tiny fraction of a proton. Unfortunately, this means that they can also detect a lot of environmental disturbances. Anything from trucks passing by to the quantum vibrations of the mirrors in the device are recorded by the detector as well, obscuring the original gravitational wave signal. Each different combination of celestial objects, like in the example, a black hole binary, or a black hole and a neutron star, or two neutron stars, all generate different patterns of gravitational wave signals. These patterns also depend on the masses, their rotation, their magnetic field, among other characteristics. The analysis of gravitational waves is therefore focused on isolating the original pattern as best as we can from the noise it is buried under. Now, how do we do this? Well, something called match template filtering, which, as the name implies, finds the best match for a gravitational wave signal from a bank of templates generated by a computer. This has many advantages, of course, but it is very time-consuming, and when the new generation of gravitational wave interferometers will be built, like the Einstein telescope, in approximately 15 years from now, we are predicted to detect over 1 million times more signals per year. This is going to be a problem. We like to call it the gravitational wave information overload problem. In order to be able to study all of these future potential new signals, a new method of analysis must be developed. Enter us, a team of students and researchers from Maastricht University and the Technical University of Eindhoven that looked at the possibility of building an algorithm that analyzes gravitational waves with the help of quantum computing. Now, you might have heard a lot about quantum computing already, but some of the true basics that you need to know are as follows. Classical computers perform operations using classical bits, which, as we know, can adopt a value either 0 or 1. Quantum computers can perform their own set of operations using qubits have special quirky quantum properties, such as superposition, where instead of being a 1 or a 0, a qubit can be in any state between those before it is measured, and the ability to be entangled, where two qubits together can have mathematical operations performed on them, such that their states are impossible to tell apart from each other. I will put more sources in the thing below to explain these whole things brilliantly. Well, but what you need to know for now is that these properties allow us to compute certain very specific tasks in a lesser amount of steps than classical computation. We are currently in something called the Noisy Intermediate Scale Quantum Era, or NISQ. And what that really means is that quantum computers are not quite good enough to be used for general purposes yet. In order to overcome this, we thought to ourselves, why don't we take two existing algorithms, one classical and one quantum, and fuse them together like some sort of Frankenstein monster? Meet the classical algorithm, singular spectrum decomposition. This mighty algorithm was designed in Maastricht University in order to decompose complicated signals into their components. If you look at its midsection, you will see the core that fuels this beast, singular value decomposition. Don't worry quite yet about what it means, but just know that we found the perfect substitute for it. Meet the quantum algorithm. The original variational quantum singular value decomposition algorithm was formulated to be used in quantum chemistry in order to find the ground state, that is the lowest energy level, of a molecule. But as it turns out, it is the perfect quantum analog for the classical singular value decomposition that fuels SSD. Both of the candidates will undergo very complicated state-of-the-art operations to be fused together, resulting in the brand new specimen, Quantum Singular Value Decomposition, or QSSD. We had discovered earlier that we could encode a gravitational wave signal downsampled to specific rates in a matrix that was 2 to the 8th by 2 to the 8th. So we put our QSSD through rigorous testing, building it so that we could decompose increasingly larger matrices. And so, our brand new QSSD algorithm rose through the ranks, until it was able to decompose a matrix that was 2 to the 5 by 2 to the 5. Still quite a bit short of the target. Nonetheless, we tried to decompose two simple sine waves that we added onto each other to see how the algorithm would perform in a real-life situation. As you can see here, the blue dots represent the original signals, with the last panel showing the sum of both of the components. The red line here shows the reconstruction of the signals that the classical SSD algorithm was able to find. In this other one, for contrast, you can find the results that were obtained by the quantum singular value decomposition. Considering that the QSSD already took over 1,000 times longer than the classical SSD to run on our computer, these results were disheartening, to say the least. Alas, not all hope is lost. There are still many other avenues to explore and ways to improve. Just because our own implementation, the specific of details of which you can also find in the thing below, was not ideal, it doesn't mean that the dream of decomposing gravitational wave signals with the use of quantum computing is dead. For example, our hybrid QSSD can be turned into a process that is entirely quantum. This saves ourselves the pesky fusion operation and the translation between classical to classical again, which takes up a lot of time. Whew! That was a lot. If you have any questions, please drop them in the comments below and I will eventually get to them. But for now, all you really need to know is that the solution to the gravitational waves information overload problem is coming, and that you, my friend, might just have witnessed the start of it. I want to give special thanks to my collaborators, Efeutku and Roberto Anwar. Thank you for everything, guys. This would have never been possible without you. And to my supervisors, Ronald Westra and Gideon Kukuk, for their invaluable help and advice along the way.